Sharma, you can say R to SPSS, sometimes Python, sometimes MOS. So all these things are very much integral part of the statistics. So good evening to all the participants. In fact, I am a regular resource person to this AKD center. And this time we are going to have a little bit of experience about R. You have already learned some basics of R, some visualization techniques like graphics, histogram, box plot, and other things. Before I start, a little bit, as I mentioned by Daya Shankarji, a little bit about myself. I'm professor in the Department of Statistics, Punjab University, Chandigarh. Chandigarh is in the north part of India, about 250 kilometers away from Delhi. And you can say about 4.5-hour journey from Delhi. I work in the area of statistical modeling, basically predictive modeling. So we have developed many models relating to cancer prediction, relating to COVID-19 predictions, and disease predictions. So all these areas I'm working into. I was also heading the Center for Systems Biology and Bioinformatics for almost 10 years at Punjab University. In fact, I established this Center of System for Biology and Bioinformatics. And that's why I was interested in the biostatistics techniques. And recently written a book also for the doctors over the entire globe. And that is called a book, Medical Statistics book. So I'm holding number of projects with ICMR, Indian Council of Medical Research, also with the WHO, World Health Organization, and some of the foreign agency projects are also with me, like Health Effect Institute in Boston, US, and then Commonwealth Secretariat in UK. So some of the other projects we are working on is International Medical Olympiad with Greece. For that purpose, we are holding a conference here in India. Earlier, we used to hold this conference in Greece. But this time we are holding this conference in India in the month of November. From 15th to 17th of November, you are most welcome to attend that conference. So I will send you the brochure. Maybe you will receive on your WhatsApp or maybe email. Okay, with this background, let me start with our topic. Topic will be correlation and regression first. So I'll share the screen and give you a little bit of theoretical background before coming to the applications of R. Okay. Just give me 1 minute, please. And if you have any questions, any query in between, don't wait till the end of the lecture. You can interrupt me anytime. Hopefully, my screen is visible. Is that okay? Anybody?
Yes.
Is the screen visible?
Yes, sir.
Yeah, all right.
Yes.
Okay. All right. So before coming on to, because the second topic will be on estimation and testing of hypothesis, but the first topic today is on correlation and regression. So I'll try to cover correlation and regression first and then move on to estimation and testing of hypothesis. So I will be delivering lecture today, tomorrow, and day after. So that's why I put the date February 28 to March 1. Of course, your program is going from 26th of February to 10th of March, right? Okay. Now, what is the most important part in statistics is to understand the nature and types of data. So I'll take 5-6 minutes before moving on to correlation regression, how to recognize different type of variables and on which kind of scale they are. So if you are having some idea, then the task will become easier. So if you look at the nature and types of data, particularly the nature of the data, it is basically of two types. Either it is called structured data or it is called unstructured data. Now, what do you mean by structured data? Structured data is the one where features can be easily extracted. For example, if I give you 100 observations, say related to height or weight or BMI, body mass index, and I ask you to compute what is the minimum value, maximum value, mean, median, mode, skewness, kurtosis, all these things can be easily computed. So idea here is that features can be easily worked out. And most of the time, the structured data is in the numeric form. But what happens sometimes? The data may not be exactly in the numeric form. It could be in the form of labels or categories, but easily convertible into numeric form. That kind of data is also counted under structured data. For example, gender. Now, gender is not numeric. It's male and female, but I can always assign certain codes, say male as 1, female as 2. Similarly, religion. You can write Hindu as 1, Muslim as 2, Sikh as 3, Christian as 4. Or if you are looking into ethnic origin, you can write Asian as 1, African as 2, American as 3, and the others as 4. So all this kind of data, which is in the form of certain labels, is easily convertible into numeric form, also comes under structured data. So what is basically structured data? Either it is already in the numeric form or it's easily convertible into numeric form. Hopefully the idea about structured data is clear. Now let's move on to unstructured data. What is an unstructured data? Unstructured data is the one where features are not easy to extract, but it contains a lot of information. For example, everybody is using WhatsApp. There are hundreds of messages, videos, pictures, right? People are talking about something. They are writing messages. But if at the end of the day, I ask you to convert this entire information into numeric form, I don't think it's easy for anyone, but it contains information. This kind of data, which is not in the numeric form, it is in the textual form, it is in the form of certain text or sentences. This kind of data comes under what is called unstructured data. So people also talk about these days big data. Big data is nothing but it could be a combination of structured and unstructured data. Of course, sometimes big data only related to structured data, sometimes unstructured data, but it could be a combination of both also. Now, as far as this program is concerned, we will not focus on unstructured data because that requires some rigorous techniques of artificial intelligence, machine learning, and data science, which is beyond the scope of this workshop. But we will focus only on structured data. What structured data means, which is in the numeric form. If you look at any kind of structured data, it is basically of two types. Either it is called categorical data or it's called measurement data. Already given you examples of categorical data like gender. You can write male as 1, female as 2. Similarly, socioeconomic class. Say lower class as 1, middle class as 2, upper class as 3. Again, it's a categorical data. Similarly, you can think of education categories. Primary school, middle school, high school, graduate, postgraduate. All this kind of data also comes under what do you mean by categorical data. And what is a measurement data? Measurement data means some kind of instrument is being involved in measuring something. For example, you can measure height with some instrument. You can measure weight with some measurements weighing scale. And similarly, you can measure cholesterol. You can measure BMI, all these things. But sometimes we do not require any instrument, but still your quantity could be measurable. Like to measure age, we don't require any instrument, but age can be measured in years. You can add months, days, minutes, and seconds, right? So hopefully the idea about the categorical data and the measurement data is clear to you. These are the examples of categorical data. For example, hair color could be brown, it could be red, black. Intentionally, I didn't put a white there because people sometimes get depressed. Our entire body is made up of 4 types of nucleotides. They are known as ATGC. So you can write A as 1, T as 2, G as 3, C as 4. Similarly, eye color can be coded as 1, 2, 3, 4. Gender can be coded as 1 and 2. Disease, mild, moderate, severe. Depending upon the severity of disease, you can write 1, 2, and 3. And genotypes, depending upon which one is dominant, which one is recessive, you can write 0, 1, and 2. So this kind of data, which was not in the form of numeric, is easily convertible into numeric by assigning certain codes like 1, 2, 3, 4, etc. This is what do you mean by categorical data. Measurement data is self-explanatory, like cholesterol you can measure, height you can measure, age you can measure. Now, if you look at any kind of measurement data, it is basically of 2 types. Either it is called discrete measurement or it is called continuous measurement. Now, what do you mean by discrete measurement? If certain isolated values are present in your data, then it is called a discrete measurement. For example, say number of members in a family. Number of members in a family may be 5 members, 7 members, 9 members, 3 members. But I cannot say number of members in a family is 3.6. It doesn't make any sense. Similarly, number of errors in the book, number of students present in the class, it is going to take certain isolated or complete integer values. So if this is the case, it's not going to take any decimal values, then this kind of data comes under what is called a discrete measurement data. And what is a continuous measurement data? Continuous measurement means it is capable of taking all values within certain specified range. For example, height can take any value in decimals also, 157.5, 157.57 centimeter. You can add third, fourth decimals depending upon the accuracy of the instrument. Age could be 62.5 years. You can add second, third decimals depending upon the accuracy, right? So all this kind of data comes under what is called continuous measurement data. All right. Now, here is something important. So far, I discussed that either there is a categorical data. If you look at the, structured data, either there is a categorical in nature or it's a measurement data. Now, knowledge about these scales is very, very important. If you are not having much idea about these scales, please listen to me carefully. There are two scales which are associated with the categorical data. What are the two scales? Nominal and ordinal. And there are other two scales which are associated with the measurement data, and they are known as interval and ratio. And people sometimes get confused between these scales. Now, if you're working in R or you're working in SPSS or any other software, sometimes many of these softwares, they will ask you, your data belongs to which kind of scale? Whether it will go to the nominal scale or the ordinal scale or the interval scale or the ratio scale. So remember, there are two scales for categorical data. What are the two scales? Let me discuss about categorical data scales. Categorical data scales are nominal and ordinal. What do you mean by nominal scale? Nominal scale means basically it's a categorical data, but you cannot order the categories. Order the category means that this will come first or this will come later. For example, look at gender. Everybody is human being. I cannot say that male will come first or female will come later. It doesn't make any sense. So you can write male as 1, female as 2, or you can write female as 1, male as 2, doesn't make any difference. Similarly, you can think of religion or maybe ethnic origin. Say Asian, African, American, right? So you can write in any order, 1, 2, 3. You can write Asian as 1, African as 2, American as 3, or you can write American as 1, Asian as 2, African as 3. It doesn't make any difference. So bottom line is, if all the categories are given equal weightage, listen to me, please. If all the categories are given equal weightage, then we say that our data belongs to the nominal scale. All right. Then comes ordinal scale. Again, this is for categorical data. And the difference between nominal and ordinal is, as the name suggests, ordinal. That means you can arrange the categories in order from the lowest to the highest or highest to the lowest. Let's look at education categories. Primary school, middle school, high school, graduate, postgraduate. All these categories can be arranged in order from the lowest to the highest. Socioeconomic class. If I'm writing lower 1, middle class has 2, upper class has 3. So 1 means the lower income group, 3 means the higher income group. So you can arrange the categories in order, right? This is what do you mean by ordinal scale. Both these, they belong to the categorical data. Now, one important point about nominal and ordinal scale is that numerical distance between any two categories, whether you are dealing with nominal, whether you are dealing with ordinal, the numerical distance between any two categories doesn't have any significance at all. For example, if I'm writing male as 1, female as 2, and I subtract 2 minus 1, it doesn't make any sense. Similarly, if I'm writing lower class as 1, middle class as 2, upper class as 3, subtract 3 minus 1 or 3 minus 2, it doesn't make any sense at all. So remember, whether you are dealing with nominal or ordinal scale, the numerical distance between any two categories doesn't make any sense at all. That's all about the categorical data scale. Now we move on to measurement data scale. Measurement data scales are also two scales. One is interval, another is ratio. Now, what do you mean by interval scale? In interval scale, sometimes the mathematical operations are not valid. For example, there are many types of data where mathematical operations are not valid. For example, let's say some beauty contest is going on, right? And there are judges, say, giving score out of 10. Let's say first person gets a score of 8 out of 10, and second one gets a score of 4 out of 10. Let me just repeat. First person gets a score of 8 out of 10, second one 4 out of 10. Now, if I divide 8 by 4, answer is 2. But no one can make such type of statement that the person whose score is 8 is exactly twice the beautiful than the person whose score is 4. Can you make such type of statements? Mathematically, it doesn't make any sense, right? Similarly, let's say one student has scored 90 marks in a test, another has scored 30. Divide by 90 by 30, answer will be 3. But you cannot make a statement that the student whose score is 90 is exactly 3 times the intelligent than the student whose score is 30. It doesn't make any sense because he may be intelligent in sports or in some other category, right? And moreover, in interval scale, 0 does not mean the absence of a character. For example, if I say temperature 0, do you think the temperature is absent? It is still better than -5, right? Similarly, if somebody has scored 0 in a test, it doesn't mean the person is not intelligent at all. Maybe on a particular day, his or her performance is not up to the mark. Next time, he or she can score better. So that means 0 has a meaning in interval scale. That's why in interval scale, 0 is treated as an arbitrary 0. Okay? And then there are problems with each and every scale. Sometimes order is not possible. Sometimes the decimal is not possible. Sometimes 0 is having some value. To overcome all such difficulties, there is a highest rating scale, and that is called the ratio scale, where all mathematical operations are valid. Let's say one person is having weight 90 kg. Another is having 45 kg. Divide 90 by 45. Answer will be 2. But you can always make a statement that the person whose weight is 90 kg is double the weight of the person whose weight is 45 kg. Nothing wrong with that. So you can multiply, you can divide. But in ratio scale, 0 means character or quantity doesn't exist. For example, if I say height 0, it doesn't exist. If I say age 0, it doesn't exist. If I say weight 0, it doesn't exist. While 0 has a meaning in interval scale, 0 doesn't have any meaning in ratio scale. So you have to be very careful. If you are still confused between interval and ratio, look at your variable. If 0 has a meaning for you, your data will go to the interval scale. If 0 doesn't have any meaning for you, it will go to the ratio scale. As simple as that. So hopefully, idea about these scales is clear. I have just given you 5-6 minutes an overview of all these scales. Yes, please. If you have any questions up to this, you are most welcome. Now I'll move on to my topic of correlation and regression. Any question, please? Any question? Yes, please. Can anybody respond, please? Are you listening to me or not?
Yes, sir.
Hello.
Yes, sir. No questions.
No questions.
No
Is it
question.
clear now?
Yes, sir. Yes.
Yeah. Okay. Thank you. Thank you so much. Let's move on to our topics of today, and that is correlation and regression. Now, remember, there are two terms. One is correlation, another is regression. Now, correlation is a separate word, regression is a separate word. Correlation means just to give you strength of relationship between two variables, or sometimes more than two variables. Let me just repeat my sentence. Correlation just give you a strength of relationship between two variables, or sometimes more than two variables. If it is only between two variables, then this is called simple correlation. If more variables are involved, then this sometimes is called multiple correlation, right? And remember, correlation is never used for prediction. Correlation is never used for prediction. Only the regression is used for prediction. It comes under what is called predictive modeling. All regression techniques like simple regression, multiple regression, logistic regression, panel data regression, logit regression. So they all comes under what do you mean by predictive modeling? Of course, correlation plays an important role in regression, but just form a part of regression. But correlation cannot be used for prediction. Okay, so first of all, I'll describe you different correlation coefficients, and then we will move on. Okay, all right. Let's look at how many types of correlation we have to deal with. So it's a complete picture of correlation coefficients. First type of correlation is generally called Karl-Pearson's correlation coefficient. It is after the name of Karl Pearson, a very well-known statistician, right? It is denoted by small r, always in most of the books. And this small r, value of this small r always lies between -1 to +1. It cannot be below -1, it cannot be above 1. So limits for r is only between -1 to +1, right? Now question is where to apply this type of correlation. So here I have written, if you see the right hand side, it is applicable only when there are two variables. One is y, another is x. For example, relationship between height and weight. And the other condition is both of them, they should be measurable quantities. They cannot be categorical. Please remember, they cannot be. You cannot say that x is categorical or y is categorical. Both y and x, they have to be measurable quantity. Like height is measurable, weight is measurable. So you can look at Karl-Pearson. Similarly, correlation between age and blood pressure. Age is measurable, blood pressure is also measurable. Similarly, correlation between, say, prices and consumption. Prices are measurable, consumption is also measurable, right? So if you have such type of data where both y and x, they are measurable quantities, that's known as both of them are metric variables. And the second condition is that there must be linear relationship between y and x. If I plot x along x-axis, y along y-axis, then if points are along a straight line, either they are increasing or decreasing, then we say that Karl-Pearson's correlation coefficient will make sense. So hopefully idea about Karl-Pearson is correlation is clear, that it is between the two variables, both the variables should be measurable quantities, and there should be linear relationship between y and x. If these conditions are satisfied, go ahead with the Karl-Pearson's correlation coefficient. Now, the second type of correlation coefficient is called Spearman's rank correlation. We have to compute all this today. Karl-Pearson's correlation coefficient and all this. What is a Spearman's rank correlation coefficient? It is denoted by rho. This symbol is called rho, RHO. And its value also lies between -1 to +1. Now, where this kind of correlation is applicable? Let's say you measure one variable on a 5-point Likert scale. Say depression is measured on, say, 5-point Likert scale. And then level of satisfaction, that is also on 5-point Likert scale. So it's already ranking 1 to 5. 1 means the lowest, 5 means the highest. So if both the variables are in the form of ranks already given, maybe depression or anxiety, both of them are measured on, say, 5-point scale, then you cannot apply Karl-Pearson correlation coefficient because they are not measurable quantities, because they are given in the form of ranking or ranks, right? Hopefully you understand what do you mean by ranks. Ranks means sometimes you must have come across pro forma where people write very unsatisfied to very satisfied, or very unhappy to very happy, strongly disagree to strongly agree. So all this kind of data comes under what is called ranking, right? Ordinal scale. So if your data is in the form of ordinal scale or in the form of ranks, you can go ahead with the Spearman's rank correlation coefficient. That is number one. Second important point. If your data is not normal, let's say your height is not normal, weight is not normal, or one of them is normal, one of them is not. You can check the normality of the data. That is also we will do today. How to check the normality of the data. There are tests. You can look at the shape of the histogram. You can draw a box plot. You can look at the quantile plot. So if your data is not normal, again, I will suggest it's better to go for Spearman's rank correlation rather than Culp-Pearson's correlation coefficient. Even when y and x, they could be measurable, but they are non-normal. It's better to go for Spearman's rank correlation. It will automatically rank and then give you the value of the row. Hopefully, the first two type of correlations are clear, and these first two types of correlations are generally used whenever we are dealing with two variables, y and x. That's all. That's why they are known as simple correlations. Now let's move on to multiple correlation. What is a multiple correlation? It is denoted by R square. Value lies between 0 to 1 because square can never be negative. It cannot take negative value. So this is a multiple correlation. Value lies between 0 to 1. In fact, R square, R is used for multiple correlation. R square is used for coefficient of determination, basically in economics, people. But anyhow, it's a multiple correlation. Now, where this kind of correlation is applicable? When there is one variable, but this variable may depend upon number of other variables. For example, yield of a crop. Well, let's say Y denote the yield of a crop. Yield of a crop may depend upon X1, that is, let's say, amount of rainfall. X2, amount of seed used. X3, amount of soil fertility. X4, amount of temperature, and so on. So if one variable, it is dependent upon so many other variables. Similarly, blood pressure. Let's say Y is blood pressure. It may depend upon age of the person. It may depend upon body surface area. It may also depend upon sometimes the fat in the body. So all these factors are responsible for blood pressure. So when there is one variable which is dependent upon so many other variables, but the biggest condition in multiple correlation is your Y, X1, X2, Xk, they all should be measurable quantities. None of them could be categorical. None of them could be categorical. You cannot say that X2 is categorical like male and female or rural or urban. No. Y has to be measurable, X1 has to be measurable, X2, Xk, they all have to be metric variable. Metric means they have to be measurable quantities. Then we use this multiple correlation, value lies between 0 to 1. Then there is partial correlation coefficient. And people sometimes ignore this partial correlation. Partial correlation is a very, very, very important correlation because sometimes there may be some variable which can indirectly affect the relationship between two variables. Let me give you an example. Let's say somebody have given you a data and data is related to age and blood pressure. Now, age is a measurable quantity, blood pressure is also a measurable quantity, and the points are along a straight line. So you can apply Culp-Pearson's correlation coefficient, nothing wrong with that. But if you are making presentation in front of some doctors, and if doctor asks you this question, that whether there were smokers and non-smokers also in your data. Now you haven't tested this part, whether there were smokers and non-smokers. How many CDs, cigarettes or BDs people are taking per day? You haven't looked into this thing, right? And clinically it is tested that those who are smokers, they are likely to have high blood pressure than those who are non-smokers. So whatever the relationship you are getting between age and blood pressure, that could be the result of smoking, which you have completely ignored. So to actually find out the relationship between age and blood pressure, you need to control the effect of smoking. And if you control the effect of certain variable, It could be 2 variables, it could be 3 variables, no problem. Then such type of correlations, they are known as partial correlation coefficients. Partial correlation is again between the 2 variables, but by controlling the effect of indirect variables which can affect the outcome. Hopefully you understand my point. Now, when you plot x along x-axis, y along y-axis, do you think points will always be linear? That means it will be along a straight line. Sometimes it may be along a curve also, first increasing and then decreasing. Or it could be first increasing, decreasing, and then increasing. So there may be curve type of relationship. If there is a curvilinear type of relationship, then you cannot apply any one of the above correlations. Then we have to go for what is called correlation ratio, eta square. That also lies between 0 to 1. Now, sometimes you have to go through the non-linear correlations also. What are non-linear? You look at the scatter plot and nothing is visible. No increasing, no decreasing trend, no curve. In such type of situation, you can only rule out the possibility of linear correlation, but there may be any other type of correlation. They are studied with the help of what is called non-linear correlations. So hopefully I have given you some idea about different type of correlations, where to use them. And for example, if you look at this picture, there is a height, there is a weight. Points are a scatter plot. These are called scatter plots. Points are increasing. So obviously you can apply Karl-Pearson's correlation coefficient. And if the points are increasing, that means if height is increasing, weight is also increasing, you can expect positive correlation between height and weight. Similarly, there could be a negative correlation. For example, if prices are high, then consumption will go down. In India, when onion prices goes above 100 rupees, people buy less onions. So when prices will increase, consumption will go down. But still it's linear. Points are along a straight line. You can still apply Karl-Pearson's correlation coefficient, but looking at the diagram, immediately you will see that there will be negative correlation between the prices and consumption. Look at this diagram. There is no increasing trend. There is no decreasing trend. There is no curve. You cannot say curve. It looks like a curve. Nothing. It's a relationship between blood pressure and hemoglobin. And clinically also, there is no relationship between blood pressure and hemoglobin. I cannot say that if blood pressure of a patient is high, hemoglobin will be low. No such thing. Right? So what does this mean? This type of correlations you cannot study like Karl-Pearson, Spearman, multiple, nothing. So here we need what is called non-linear correlations. But we will not cover non-linear correlations. They are beyond the scope of this workshop. Okay, these are not the only correlations. There are some other different type of correlations. If you remember, I discussed about the categorical data scales. I discussed about the measurement scales, categorical data scale, nominal and ordinal. Let's say your one variable is nominal, another is also nominal. Examples I can give you. Let's say example is gender. Gender is nominal. And the blood types are also nominal. A positive, O negative, something like that. And you are looking at relationship between gender and blood types. So none of the correlations which I discussed previously, like Spearman's or Karl-Pearson or multiple or correlation ratio or none of them is going to work. Then which type of correlations to be computed? So these are the correlations to be computed. Contingency coefficient, phi and Kramer's V, lambda, uncertainty coefficient. Out of this, uncertainty coefficient is the best one. Right? Similarly, if you have ordinal by ordinal data, one variable is on ordinal scale, another is also ordinal scale. Let's look at the example. Say level of satisfaction, very unsatisfied to very satisfied on a 5-point scale. So it's ordinal. And on the other side, you have income. Say income less than 20,000 rupees, 20,000 to 40,000 rupees, 40,000 to 60,000 rupees, and more than 60,000 rupees. This is again ordinal, because you can arrange the 1, 2, 3, 4, 5. You can arrange the categories of income in order. So it's ordinal by ordinal. In such type of situation, again, you cannot compute the previous correlations, but you can compute gamma, you can compute Somers D, you can Candle stop. Out of this, the gamma coefficient is best. And sometimes we have to deal with nominal by ordinal. Let's say one variable is nominal, like gender. Another variable is ordinal, like severity of disease, mild, moderate, severe. It's ordinal. Mild means the lowest, severe means the highest. And you are looking at a relationship between gender and severity of disease. Then you can apply this very important test in statistics that is called chi-square, right? And unfortunately, people also apply chi-square for nominal by nominal data, for ordinal by ordinal data, which is absolutely wrong. Even statistics people also make mistakes. And if you have nominal by interval or ratio data, like you have a gender, male and female, on other side you have blood pressure. It's one variable is nominal, another is on interval scale. Then which are the correlations to be computed? Kappa, risk, McNemar, eta. Out of this, eta is the best. Eta is the best coefficient, right? So all these correlation coefficients, whenever we deal with the categorical type of data or mixture of categorical and measurement data, then these are generally not called correlations. They are covered under what is called measures of association. So these are called measures of association. Okay. All right. So this I have already discussed. Now, where to apply Karl-Pearson's correlation coefficient? For example, here points are increasing, here points are decreasing on the left-hand side. Points are along a straight line, points are along a straight line. So you can go for Karl-Pearson type of correlation. But look at this picture. Here first points are increasing, then decreasing. Here there is exponential kind of trend. It's along a curve. So it's a curvilinear relationship, not linear. So you cannot apply Karl-Pearson, but you can go for correlation ratio, or maybe quadratic or cubic relationship, or exponential relationship, or log transformation relationship, etc. Now, what is the idea of strong and weak relationship? If your points are very, very close, in a scatter plot, then we say that there is strong relationship. Similarly, this is a strong positive relationship. This is a strong negative relationship. But here also points are along a straight line. Points are also along a straight line. But they are having certain kind of errors. They are known as measurement errors. So obviously, you can think of Karl-Pearson type of correlation, but this will result into weak relationship. Here the correlation may be 0.8, 0.9, but here the correlation may be 0.4 or 0.5, right? Similarly, but it will be positive and this will be negative. Okay. So we have discussed about Karl-Pearson's correlation coefficient, Spearman's rank correlation coefficient, multiple correlation, partial correlation also. Now we move on to regression. And in the last part, in 1 hour, I'll give you how to do all this in R. Will that be okay? Yes, please. First of all, I'm completing the theory and then I'll go for the practical demonstration. Will that be okay?
Yes, sir.
Yes, sir.
Any question up to this in correlation, if you have, or in measurement scales? If you have any question, you are most welcome to ask. Yes, please. Before I move on to regression. Any question?
Sir, please give, sir,
Yes.
please give some examples of curvilinear relationship.
Give some examples of
Curvilinear relationship.
curvilinear relationship. Curvilinear relationship can occur. Let's say y is equal to x square. Y is equal to x square. Suppose you take values of x as 1, 2, 3, 4, 5. Then what will be the value of y? Y will be 1 square will be 1, 2 square will be 4, 3 square will be 9, 4 square will be 16, 5 square will be 25. So if you plot on x-axis, you are having 1 to 5. On y-axis, you will be having first 1, then 4, then 9, then 16, then 25. So it will increase exponentially. It will increase. So it will not be a straight line. It will along a curve. So if you have such type of relationship, that kind of relationship is called curvilinear relationship. Similarly, if you look at, let's say when the child is born, and let's say we take age from 0 years to let's say 70 years, right? So when the child is born, initial 2-3 years are very difficult. Why? Because immunity is low, and many children, they die also during this period. So some children may die, but as the child grow up to the age of 6, 7, or maybe right up to 30, there are little bit chances that a person is likely to die unless there is some major problem. But after 30, then again problem starts, like somebody can develop diabetes, somebody can develop blood pressure, somebody can go for a cardiovascular disease. Then again, so sometimes the graph will start from the lowest side and then it comes to the normal, then it start declining. So that kind of relationship becomes what is called curvilinear relationship. Hopefully you understand what I'm saying. Yes, please.
Okay, sir. Thank you.
Yeah.
Thank you.
So let's move on to regression now. Now, as I mentioned, regression is the term which is used for prediction, not the correlation, right? So we will, in your syllabus, it has been mentioned 2 types of regression. One is simple regression. Another is multiple regression. What is a simple regression? Simple regression means it is involving 2 variables. One variable is dependent, another is independent. For example, weight may depend upon height. If height will increase, weight is likely to increase, right? Similarly, blood pressure may depend upon age. If age will increase, chances many people are, they are having old age, they are having BP problems, right? So that kind of situation. So only two variables, one dependent, another independent. So it's a problem of simple regression. Then what is a multiple regression? Multiple regression, I'll explain you. First, we'll go through the simple regression. So this I'm explaining you simple regression. So linear simple regression is a statistical procedure for predicting the value of dependent variable for a given value of the independent variable. So our model look like this. That's y is a dependent variable. In the 10th standard, you must have gone through equation of a straight line. What was the equation of a straight line? Y is equal to mx plus c, if you remember, right? Where m was called the slope and c was the intercept, if you remember. That is the equation of a straight line. Now, if you compare that equation and remove this epsilon I, which is in the end, this is c plus mx. Just forget about y is equal to c plus mx, where c is your beta naught and m is your beta 1. So it's just like a simple equation of a straight line. Then we are adding this error. I'll explain you what is the meaning of this error. This error is sometimes called measurement error. For example, if I ask you to measure the height of a person, you give your answer as 157 centimeter. I ask the another person, please just tell me the height of this person. He can go up to 1 decimal. He says, no, sir, it is 157.1 centimeter. Another person can go to second decimal. So there are always measurement error. If you are going for a laboratory test, let's say test of certain parameters of your blood. If you go for a testing in one lab, you will get hemoglobin, TLC, DLC, all these values, and get it done from the another lab too. Do you think they will be exactly matching with each other? There may be a little bit of variation. That variation we capture under what is called epsilon I, right? So that's why we are not writing a straight line. We are writing in statistical modeling beta naught plus beta 1x plus epsilon I. Now, if epsilon I will be 0, then it will be a perfect model. All the points will be on the line. But generally, it doesn't happen in real life. So your y is a dependent variable, x is an independent variable. This is your slope, this is your intercept, and this is error. So we have to minimize this error. Our problem is to estimate these 2 parameters. These 2 are called parameters beta naught and beta 1. And from the given observations, we can estimate them. So here is the complete picture. This is your dependent variable. This is intercept. This is slope. And this is independent variable. And here is the random error, which is beyond your control. sometimes measurement error, right? It is likely to happen in any experiment. Okay, so simple linear regression is only having two variables. One is X, another is Y. Okay, so what is that error? Epsilon. For example, if 6-7 points are there, you can see these points, scatter plot. Now, if your point is exactly on this line, green line is the line of prediction, best prediction we call this, right? And what is intercept? This beta naught is nothing but wherever this line, green line, is going to cross the y-axis, then the distance from origin to that crossing point is called beta naught. You can see that. So crossing here, and this distance from origin to this point is called beta naught. And if you drop a line parallel here, then this angle which is being formed is called slope. Because your line could be like this, your line could be a little bit more parallel, then slope will be less. If it is high, then slope will be high, right? So line is represented by two factors, basically, intercept and slope. That's all, right? Then if, let's say for this point, if it is exactly on the line, error will be almost negligible. Similarly, for this point, error will be almost negligible. But look at this point. This is slightly away from this line. So this will contain some error. Similarly, this is having far away. So this is having error. So this is what do you mean by this error? Hopefully you understand what is the meaning of this error, right? This is the line of best prediction, which we have to draw today. What is the line of best prediction? In R, it is known as AB line. A stands for intercept, B stands for slope. Okay. Now, from the given observations, we can get these estimates. Error will go to 0. Let's say estimate of this B naught is, beta naught is B naught. Estimate of beta 1 is B1. So you will get this type of equation, prediction equation. So this will be estimated from the given data. This will be estimated from the given data. These two values will be known to you. Now you give any value to X, you can predict Y. You give any value to X, you can predict Y, right? Now how this parameters gets estimated? So there is a mathematical principle that is known as principle of least squares. It consists in minimizing the error sum of squares. Now let me give you a simple example of a regression model. Let's say in my class there are 30 students. I enter the class. There are 30 students. I'm having a weighing machine with me and also having a measurable tape. So, but on that particular day, out of the 32 are absent. 2 are absent. So I measure the height and weight of each and every individual. Suppose Y represents your weight, X represents height. So I'll call the first person weight, measure its weight, that is Y1, also its height, that is X1. Similarly, the second student, Y2, X2, third, Y3, X3, and so on. So you will be having 28 observations of Y and 28 observations of X. And they are present in pairs. Pair means they are basically related to weight and height, weight and height. Y is weight, X is height. Okay. Now, based on these 28 observations, I form an equation. And equation will look like this. Equation will look like this, where these values are known to you. Let's say this value is 5, this value is 6. This value is 5, this value is 6. Now, this equation is with me. Now, next day when I enter the class, the 2 students who were absent yesterday, now they are present. But weighing machine is not with me. But somehow I can measure their height. And X represents height. I measure the height. Suppose it is 167 centimeter. So I multiply with this, which this is known to me. Add this, you will get the corresponding weight. Similarly, you can measure the height of the second one, substitute in this equation, you can get the weight of the second person without weighing machine. So this is what do you mean by prediction. So without weighing machine, you can predict the weight of a person. Hopefully the thing is clear. Yes, please.
Yes,
Correct.
yes.
Okay. Now let's move on to the last theoretical part. Then I'll give you a practical example. We call this as, this is called a simple linear regression model. This one. Up to this, it was simple. Why simple? Because there are only two variables. One dependent. This one, y is dependent, x is independent. But there could be situation of multiple regression where there is one y dependent variable, and there it may depend upon number of x values, x1, x2, xk. Already give you an example of yield of a crop. Yield of a crop may depend upon amount of rainfall, amount of fertilizer, amount of seed, amount of temperature, amount of soil fertility. So all these are k independent metric variables. The biggest restriction in multiple regression is, right, the biggest restriction, just make it slightly better here, where these are estimated, and r square. Yeah, now you can read this clearly. Okay. Now you can see. So it's an extension of simple to multiple. So y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta k xk plus some error. Right. Now, if you stop up to this place, it's just a simple linear regression equation. Y is equal to beta naught plus beta 1 x1. But here you can add x2, here you can add x3 going up to xk. So if you do it, then it becomes what is called multiple regression model. Multiple regression model. Let me put this as multiple regression model. Okay. Multiple means you are dealing with multiple independent variables. Of course, dependent variable, just like in simple regression, is one. Here also it is one. Then again, we apply the same techniques. We minimize this error sum of squares. We get the estimates of this beta naught, beta 1, beta k from the given data. And finally, you can estimate this. Estimated equation will be this, where these values are known. Now you give any value to x1, x2, xk. If somebody asks you that if your amount of seed is this much, amount of rainfall is this much, amount of fertilizer is this much, amount of soil fertility is this much, what is the expected yield? So that can be computed from this equation. So that's why this is called multiple regression, generally called multiple linear regression model, right? Multiple linear regression model, where these are estimated from the given data. So here we will see value of r square, adjusted r square. Now, very important point. Let me just make it bigger screen. Very important point, which you can understand. Now, out of the k predictors, these are called k predictors, x1, x2, xk. Do you think all will be important to predict y? Not necessary. Maybe out of the k, only 3 are important to predict y, or maybe 4 are important to predict y, or none of them is important to predict y, or all of them could be important to predict y, right? So that means we have to see which variables are important to predict y. There could be a variable which are non-significant. Then why to include them into the model? We should exclude them, basically. We should exclude them, right? So our first question comes, out of the k predictors, which predictors are most important, right? And for that purpose, we go for what is called stepwise regression. So today I will go for the stepwise regression. Stepwise regression is generally in R is called update model, and update model will just remove insignificant variables from the model, and it will retain only the significant variables in the final model. And that is our requirement. Not only that, when we apply stepwise regression, it will give you the hierarchy also, that which variable is the most important to predict y, whether x2 is most important or x1 is more important or x or any other is important. So if x2 is more important, x2 will come first. Then comes, let's say x5 is important, then x5 will come. Then suppose x1 is important, then x will come. So this is the job of what is called stepwise regression. So it will identify which variable is the most important to predict y. So two things in stepwise regression. One is out of the K predictors, how many independent variables are important? Number two. It will give you a hierarchy, which variable comes at number one, which variable comes at number two, which comes at number three. All right. So this is what do you mean by multiple regression model. So now the theoretical part is done. I will move on to practical part. If you still have any questions to ask me, yes, please. Any question? In multiple regression, simple regression, correlation. Yes, please. Any question you want to ask?
In here, you mentioned the R squared and adjusted R squared. Are there any difference between?
Yes, there is a difference. I'll explain you while the output will be there. So whenever we apply this multiple regression model, two things will appear. One is called R square, another is called adjusted R square. Adjusted R square is basically adjusted for degrees of freedom, right? But to report both of them is very, very important. Because if you are simply reporting R square, you are not giving the complete justification to the model. You have to report R square as well as adjusted R square. So when output will appear, I'll explain you what is the actual meaning of adjusted R square. Will that be okay, madam?
Yes, yes.
Yeah. Okay. So I'll open a practical file and then start with the working of R. You are hopefully you are already familiar with the R, and I'll open this. I have given this name as workshop AKD because this is AKD center, AKDAR center, right? And I'll open this where I have certain inbuilt commands written over there, and I'll start so that you will not have to type and do all the things. I'll send you this file later on and you can work on this file. Okay. Now, whenever we start working in R, hopefully you can see the screen. Yes, please. Is it visible?
Yes.
Yes. You know all the four panels. Here you can write your programs. Here you can, this is a console. And then this is your, where you can get your objects. And here you can get the graphs and other things, right? Packages, graphs, and many other files which are there in R, they're also there. Okay. Now, the first important point while working with R is to open your folder. For example, I have made a folder with the name of AKD Center. AKD, I have written this just as AK Das because this is AK Das Center. So I have made on the desktop. You can see this AKD. Can you see that? Yes, please. Hello?
Yes.
Yeah. So always make a folder and keep all the files in this folder. Hopefully somebody may have told you that whatever the files you want to use, you always keep this in your folder. So I have kept all these files which I'm going to use, maybe today, tomorrow, day after. I have kept all these files here. What is the advantage of keeping all the files in your directory? Because you will not have to go for the path again and again, that pick up this file from AKD. You can simply, once you are connected to your folder, so you can access in one command simply your file, right? So that is the advantage of this AKD. So I have made this folder AKD, and I'll move on now. Okay, so here we were. So get working directory. Let me see the working directory. It says you are already into your working directory. If you are not here in your working directory, then this is how you can link this working directory. Say set working directory, SET means set working directory, and give the path. Path I have just copied from here, just like this. You go to the properties here and you can copy this path. This is the path. This is what I need to copy, right? Copy this path and paste it here, and you will be, I have just pasted it here, and then reverse this symbols, right? Because as R doesn't understand this, it will understand backslash only. So this is backslash, not the front slash, and then AKD. So you will be in your directory. If you are So this is how you can connect to your directory. So run this. Now again, check whether you are into your directory or not. So you are into your directory. Is this clear? Hopefully everybody knows about this. Yes, please. Is this okay?
Yes.
Yeah. Now, sometimes we can enter a single value. You can enter vector of values. For example, I mean, before coming to correlation regression, so that you can have a good hand on R. So creation of data vector. How to create data vector? Suppose I want to store all these values in X. So how to store this? With the help of this, which is called combine or concatenate, right? This C, 2, 3, 4. So how many values are there in X? You can see these are the values in X. And if you want to see how many total observations are there, you just give length. So it will give you that there are 10 observations. If you want to take the sum of this, simply give sum X. So you will get sum. If you want to get the mean of this, simply give mean X. So you will get the mean. If you want to see the minimum value, so this is the minimum value, right? Then you will see the maximum value. So you can see the minimum value was 2. That you can see from here. 2. Maximum value is 10. Right. You can also look into range. Range means the minimum and maximum value. So minimum is 2, maximum is this. Similarly, median value you can check. So this is the median, 6.5. Different quantiles can also be computed. For example, 0th quantile, 25th percentile of the data, 50th percentile of the data. So all this, for example, if I run this, so 50th percentile is nothing but median. 50th percentile is nothing but median, because it comes halfway, and you can see median and they are same. But 25th percentile or 26th percentile or quantile is nothing but value is 4.25. What does this mean? That 25% of the observations are below this point, 4.25, and 75% above this. While 75% means 7.75 means 75% of the observation in your data are below or equal to the point of 7.75. Only 25% are above this. So that this is what we mean by. But if you give the summary command, it will give you all minimum value, maximum value, first quartile, median, quantile, etc. Similarly, you can go for sorting of the data by using this command, sort X. So you can see all these values have been sorted in this. Similarly, reverse sort X. Reverse means in the reverse direction. This is sorting from the lowest to the highest, and this is in the descending order. So this is increasing order or ascending order, and this is decreasing order, right? Similarly, you can compute log of X, all these values of individual values of log X. Log to the base, this is natural log, log to the base E. Similarly, if I want log to the base 10, so you can give this command, all these values. Log to the base 2, generally bioinformatics people, they use log to the base 2. And then if I add 1 plus X, then 1 will be added to all the values of X. If you remember, our first value of X was 2, 3, 4. So now values will become 1 plus X means it will become 3, 4, 5, right up to 11. You can check this. So 3, 4, right up to 11. Similarly, if you can multiply each value with 2, so you will get 4, 6, and this, right? Similarly, you can also compute log of 1 plus X, log of 2X, square root of X, X square values, and then you can take sum of X, right? Then you can also look into X. Now you can easily, yes, please. Hello, can you repeat your sentence, please? Hello? Somebody was saying something. Can you repeat, please? I'm here. Yes, please. What do you want to say? No question? You can unmute yourself and say something. Okay, should I proceed further? Yes, please.
Yes.
Yeah, okay. So you will be here at the screen. Can you see my screen again? Yes, please.
Yes.
Yeah. Now you see the important point in R. You can always, we used to calculate under root of R. We used to calculate cube root of R. But beyond cube root, the things becomes difficult. But in R, you can raise anything. For example, x raised to power 0.32. Now, nobody can do this calculation, x raised to power 0.32. But R will do it in fraction of seconds. All these values are of x raised to power 0.32. Similarly, if I want, first it will compute x raised to power 0.32, and then you can take the sum. Right? Similarly, you can go for computing of skewness and kurtosis. Skewness means lack of symmetry. Kurtosis means whether your graph is highly peaked or it is flatter. You can check with the help of that. For that, we require a package that is called moments. So I need to install this package, which is called install.packages moments. And you take this package to your library then. Hopefully somebody must have discussed all these things because you have already gone through the sessions of R. I'm just repeating certain things before moving on to correlation regression. Let's say this data vector is given and I want to compute its skewness and kurtosis. It requires a moments package, which I have already uploaded, right? So I'll give this. So all these values are there in X. So if you give skewness X, this will give value of beta 1. So this is the value of beta 1. Beta 1 is coming out to be negative. That means negative means it's negatively skewed. Your data is negatively skewed, right? That means more values are on the left-hand side. Your mean is also on the left-hand side. Similarly, you can compute kurtosis. Kurtosis measure the peakedness of the curve. So this value is positive value. So that means it is having high peak. You know the normal curve. So it's slightly having high peak than the normal. This is what it means, right? Similarly, there are two important commands in R, which is called rbind and cbind. Rbind combine the objects row wise. That's why it is called rbind. R stands for row. And cbind combine the columns in column wise, right? For example, if you write 3 values, 1, 2, 3 under this X, 3 values under Y, say 4, 5, and 6, and I give this A is equal to C bind XY. So what will appear in C bind XY? If you look at A, it is a column wise binding. That means your X will be in one column, Y will be in another column. This is called column wise binding, right? Similarly, if you use this R bind, it will be row bind. First row 1, 2, 3, second row 4, 5, 6. You can check that. So this is row bind and this is this. Okay. Now this was the column wise, this was row wise. Similarly, another example you can think of is called how to construct this data frame. We generally call this as data frame. Data frame means you have to put all your table values into one table, and that is basically called data frame. For example, I have this value. Length means height basically. Height is 180 centimeter, 175 centimeter, 190 centimeter. Weight is your 75, 82, 88. Name is, first person's name is, so this is a character variable. This is a numeric variable. Whenever you are writing numeric variable, you don't require to put in quotes. But if you are writing any character variable, let's say first person's length is 180 and weight is 75. This person is Anil. Second person is Ankit. Third person is Sunil. And now I make a data frame. Data frame of this type, data dot frame. This is the command to be used. Friends, data frame, data dot frame. First is a name, then length, and then weight. Right? Let's do this and see what will happen. So you are having length variable, weight variable, name variable, and now you are having friends. So your name of the data frame is friends. So click here, you will see a table. First, because we have the first element of the data frame as name, so name appears at number 1. Then we have the length appears at number 2. Weight appears at number 3. Similarly, you can go on adding other variables like BMI, skin fold thickness, chest measurement, cholesterol, whatever you want to add, right? Now, obviously, these variables are in a frame. They are not individually available to you. Of course, we have fed them right here, but if you would have taken from this some file, they are not, individual values are not available. But here it is available because we have written these values. If these are not available, you need to extract. How we extract? For example, I want to extract names. So whatever is your data frame is now friends, $ name. So name will be now separate. So name you able to extract the name. Similarly, length, again friends length, again weight length. Now weight, length, they are values individually available. So you can compute mean weight now. Otherwise, sometimes you cannot compute. Okay. Now moving on to next. Sometimes we create a data vector. This is the data vector. And something goes wrong. Let's say here it was 1. It should have been 4. Then you delete the entire vector and redo it, but there is no need. You can use this command, which is called data entry, and you can make a correction, right? For example, I look into this. So these are the values. Let's look into data entry, X. So data entry X will open. So this screen will open. You can see. And I make, let's say, changes in place of 1. Suppose I make this, I want to make this, suppose 20. I want to make this 20. And then simply close this. And then again print this X. Now you can see. Okay. Data entry. What happens? Just a minute. Something went wrong. It's not coming up. Let me open the file again. There is something wrong. Just give me 1 minute, please. Sometimes it happens because I'm using this computer since morning. So just give me 1 minute. I'll open the file again. Don't worry. You will be the same thing. Just wait for a moment. Just opening that file again. Okay. So I'll just run this again. So all these things I have explained it to you. And we were at data entry. This section, data entry. So I enter here, then data entry. What's happening? Okay, I need to close this. It's giving some problem. All right. So if you change one value, you can see 20 will appear. I don't know. I mean, there is some problem here. Let me try once again. So let me write. This is your X value. All these X. Now let me data entry. Data entry and change this. Suppose I make this 2 value as 20. And then close this. And then print X again. Now you can see that 2 value has changed to 20. Can you see that? Yes, please.
Yes.
Yeah. Okay. So this is how you can change any value, right? Now we are moving on to, with this, all these basics, I'll move on to what is called correlation and regression. So this is correlation. First we will do correlation and then we will move on to for regression. Okay, let me enter 2 vectors. They should be of the same length. So this is your X vector, this is your Y. So let's say these are some values. Now, how you can see they are of the same length? You can check with the help of this LENGTH. Let's say length X. And similarly here, let's say length Y. Say length Y. So you can see how many elements are there in this. 11 elements in X. Similarly Y. And it should be 11 elements in Y. Otherwise, you cannot compute correlation because correlation is only between the pairs. Hopefully you understand. Let's try to find out correlation between y and x. Correlation between y and x. So simple command is COR x and y. Similarly, if you go for the plot, let me go for the plot. Let's say plot x comma y. Plot x comma y, and you can see a plot of this type. So points are increasing. Here you can see points are increasing. So that means you can go for Karl-Pearson type of correlation, and you cannot expect very strong relationship because points are scattered, but they are increasing. You can go for Karl-Pearson type of correlation, right? So by default, R will give you Karl-Pearson. For example, if you compute correlation, so this is the value of correlation. It says correlation value is 0.742. It has to lie between -1 to +1. And scatter plots shows that points are increasing. That's why your correlation is positive. Your correlation is positive. Now, this is basically Karl-Pearson's correlation coefficient. Suppose I want to check whether this correlation coefficient is significant or not. So we can further go for testing, and that is given by correlation dot test x and y. So if you do this correlation testing, you will get a p-value. So this is your p-value. Again, the same correlation, that is 0.74. This degree of freedom will be n-2. N-2 means if you have 11 values, so degree of freedom will be 9. And correlation is tested based on t-test. Formula is r upon under root of 1 minus r square into under root of n-2. That is having t distribution with n-2. You will not have to remember that. Only thing is you are concerned with the p-value. So your p-value is 0.008, which is less than 0.05. As long as your p-value is less than 0.05, that means result is significant. So what was H0 here? H0 null hypothesis was that there is no relationship between x and y. That was our hypothesis. Alternative, there is a relationship. Now it says whenever we say p-value is less than 0.05, H0 will be rejected. What was H0? There is no relationship. That is rejected. Alternative will be accepted. What was alternative? That there is a relationship. So you can say whenever we say p-value is less than 0.05, alternative will be accepted. That means the results are significant. Okay, results are significant. So that means there is a significant relationship between y and x, and the amount of correlation is 0.7424. Now suppose instead of Karl-Pearson I want to compute Spearman. Then you just need to write one method here. The method is equal to, in quotes you write Spearman, so it will compute Spearman. Again, correlation between x and y, but with Spearman's method. So this is Spearman's. You can see slight change. Spearman's correlation is slightly higher than Karl-Pearson. That was 0.74. This is 0.76, but doesn't matter, right? So this is how to compute the simple correlation between this and this, right? So I'm trying to get one more example for you. Let me now, our directory, this is our data actually, correlation.csv. So I'll import this data. You know how to import the data from Excel. I'll show you the data, which kind of data it is. This is the data I'm talking about, correlation. So there is a gestational age, and then there is a birth weight. Gestational age and birth weight. You see, normal period of a delivery is 9 months. 9 months means 37 to 41 weeks, right, for ladies. And that period is basically called gestation period. But sometimes there are premature babies. And if there are premature babies, obviously birth weight will be less. And if birth weight will be less, birth weight of the baby is less, then what will happen? Baby has to face a lot of challenges. He or she has to be put into incubator. Artificial feeding is required. So many things. Immunity will be low and a lot of complications. So normal birth period. Normal birth weight is around 2.8 to 3 kg. If the child is between 2.8 to 3 kg, or maybe more than 3 is okay, no problem. It could be even 4 kg, no problem. But that is a normal period from 2.8 to 3 or 3.2. But if babies are before that, then that is called problem of low birth weight, right? So there is a gestational age, there is a birth weight. Now, somebody want to predict that what could be the birth weight. Let's say if gestational age is only 29. Now 29 doesn't appear here. If gestational age would have been only 29, normal gestational age is 37 to 41 weeks, right? So let's say if somebody asks you this question, it is 29.3. Let's take 28, right? If somebody asks you this question, if gestational age would have been 28, what could have been the corresponding birth weight? So you want to predict. For that, we require regression, right? So first of all, we will see the correlation between them, whether there is any correlation between birth weight and gestational age. I'm closing this file. Okay, so that file is here. I will import. How to import this file? Into R. So this is the command data read.csv, because always convert your file to the CSV file if it is an Excel file. That will make task easier. Otherwise, you have to load one package of XLS read one, and then you can load your Excel file also. But generally we load CSV file. So this was the file correlation.csv. So I'll import this file. I have just given the path copied from there, and after AKD I have written corr.csv. So now data is there. I can see head data means first 6 rows of the data. So you can see the same data, gestational age and birth weight, right? Gestational age and birth weight, first 6 rows. Now, if you attach data, then you will not have to extract the data. Because if you simply write attach data, so all the individual values will be available. Gestational age individual value will be available. Birth weight individual value will be available. So let me do this. So this attach data. Then I'll go for plotting. I'll remove this plot from here and go for the plotting of gestational age versus birth weight, with main title at gestational age is birth weight. GA stands for gestational age, BW stands for birth weight, and subtitle is gestational age in months. Limits I have fixed from 1000 to this, and I'm saying that column should be red and subtitle should be blue. Main column should be red and the subtitle should be blue. So with this running here, you can see it is blue, it is red, and this is the picture you can see of gestational age versus birth weight. Now immediately you will come to know that again there is an increasing trend. There is an increasing trend, right? And then you can go for the testing of this. So here itself you can go for correlation test between gestational age and birth weight. So it will give you this value. So this is a p-value. P-value means 6.13 into 10 raised to power minus 5. So it's very 0.00000 something, right? So that means p-value is less than 0.05. So if p-value is less than 0.05, your result is significant. So there is a significant amount of correlation, and that is 0.82 approximately. So amount of correlation is 0.82, right? And it is positive. So that means birth weight definitely depends upon gestational age. As the gestational age will increase, birth weight will also increase, right? Now let's fit a model. Now we are coming to regression part. Please, now I'm going to regression analysis. So let me call this as regression analysis. Regression analysis. So if you go to regression analysis, so this, let's say, call this model as fit model. You can write anything. You can write model here. You can write fit here. It doesn't matter. This LM stands for linear model. Linear model, that means I want to regress. Regress is that variable which is on the left-hand side. Y on X. So if you remember the equation, Y is equal to beta naught plus beta 1 X, right? So y was on the left hand side. So your birth weight, whatever you want to predict, always on y-axis. That is your left hand side. So birth weight on gestational age. So birth weight, then use this tilde sign, tilde gestational age. So it will regress your birth weight on gestational age and you will get a model. So let's regress this. So it has run. And if you give this command summary fit, you will get the output. So here is the output. So this is the output. It has called this function and then coefficients are there. These are the coefficients, right? And from here, you can write the complete equation. I mean, you want to birth weight is equal to, this is the value of beta naught, which has been estimated. So value of beta naught is this. Control C, I'll put it here. Control V, sorry, not here. Here. Control V plus. And the second value is this. Control C, Control V, multiply with gestational age. So this is your predicted equation. Hopefully you understand what I'm saying. So if you give, let's say somebody asks you this question, gestational age would have been 28. Right, I call this, let me put this into this. So this is the line you are getting. So I'll put gestational age value as 28, multiply by 180, minus this factor, you will get the birth weight of the baby. So that's why this is called prediction. And then you can draw this line also, how this line goes. And that line is called AB line fit, AB line to this model, or AB line to this fit, right? AB means A stands for intercept, B stands for slope. So it will plot intercept and slope. So here is the answer. So that is intercept and slope. Right? So this is the value, what you are getting, AB line fit. Okay. So if you have any questions, please, you can ask me. If you have any questions up to this, I have completed the simple correlation and simple regression. And the last part in next 20 minutes will be about multiple regression. Theoretical part we have already done. Yes, please. Any question up to this? Hello?
Excuse me, sir.
Yes, please.
Sir, can you please repeat the function of AB line fit?
Can you repeat again?
Can you please repeat the function of AB line fit?
Again?
AB line fit function. What's the function?
Repeat. Okay. Okay. Let
Yes,
me do it for this only, for some other purpose. Let's say there is a value of X, there is a value of Y, and I want to fit this model, linear model, Y regressed on X. So I'll do it here and get the summary model. So from here, again, you can write down the equation. Can you write down the equation from here? Yes, please. Madam, आप लिख सकते हैं कि नहीं?
Yes, sir.
हाँ, कैसे लिखेंगे बताइए? That Y is equal to 29 point.
MX plus C4.
Yeah, Y will be equal to
20.
constant 29.9165.
Yeah. This will be plus. Hello?
Yeah. And let me plot this. You are saying plotting. Let me plot X and Y. So this is X and Y plot. And now AB line of the model. This is your AB line. Can you see that? Yes, please.
Yes, sir.
Yeah.
Yes,
So
sir.
AB line means that is the line of best fit. Okay. Now,
Okay.
there is important point here. You can also look into confidence intervals of the coefficients. That is given by this coefficient model, confidence interval for model. So if I want to see the confidence intervals for intercept, that is minus 8.3 to this. Confidence interval for the slope, 0.25 to 1.34. So that is the 95% confidence interval, lower and upper, right? Similarly, you can look into other attributes of the model because we have given the name as model. So at other attributes, you can see from here. You can see all fitted values. You can go for QR plots. you can go for other things can also be looked into. For example, if I write model dollar coefficients, you will see the intercept, you will see the coefficient of slope. So this was the coefficient for intercept. This was the coefficient for that we have already seen. You see 29.91. Similarly, you can see all fitted values. Suppose I model fit values. So these are all fitted values, fitted by the model. One is the actual value now. Another is fitted by the model, right? Fitted by the model. And then you can go for the residual. What is a residual? Residuals are nothing but the difference between actual and predicted values. So that is the difference between actual and predicted values, right? So this is all about the simple linear regression. Now we move on to multiple linear regression. So here is the multiple linear regression. In last 20 minutes, I'll give you, and that will cover up correlation and regression today. And tomorrow, we will start with estimation and testing of hypothesis. Estimation and testing of hypothesis. And with theoretical background and then practical examples using R. Okay. First, I'll show you this file. You see, because we are already into our directory, so even if you don't give this path, it will read automatically. It will read this file. There is no need to give path again and again because you are already linked to your directory, right? So I'll show you the file and then we will move on. Where is this file? It says multiple. This is the file. So it says a real psychology problem, basically, problem from psychology. And psychology people, generally they want to estimate IQ. This is IQ. So this is your Y, dependent variable. Please try to understand the nature of the data. This is your IQ. IQ is Y. And it depends upon number of other factors. One of them is mental age. That is X1. Anxiety, X2. Depression score, X3. Stress, X4. Communication score, X5. Convolution score, X6. So basically, you want to predict IQ, which is your Y, and it depends upon how many predictors? 1, 2, 3, 4, 5, 6. So it depends upon 6 predictors. If you take only first two, IQ and mental age, it becomes a simple linear regression model because one will be dependent, another will be independent. But here you have multiple independent variables. Multiple independent variables. One is X1, X2, X3, X4, X5, X6. So there are 6 predictors. Yes, please. Is the data clear? Hello?
Yes, sir.
So it's a problem of multiple regression. Problem of multiple regression. What do you want to predict here? Yes, please. Anybody? What do you want to predict?
Level of the person.
Yes, please.
IQ
Madam,
level
क्या
of
बोल
the-
रहे हैं आप?
Yes, IQ level of the person.
Yes, IQ level of a person based on all the 6 predictors.
Yes.
Mental age, anxiety, all the. So it's a problem of multiple regression. I'm closing this file. Hopefully the data is clear. File is multiple.csv. So I'll import this file without giving any file name. So here it is, multiple. I have put this into my folder so I can directly access from there. So here is multiple.sys. So simply give this command, your data will come. So this is your data. You can check your data. Same data. IQ, mental age, anxiety, depression score, stress. You can just look at the first 6 values so that you can go for the headings clearly. Is that okay? Yes, please. Head will give you first 6 values. Tail will give you last 6 values. For example, if you want all the tail values, you can give the command tail data. So you will get the last 6 values of the data. So these are the last 6 values of your data. So tail and head will give you this thing. Is it clear, madam?
Yes.
Hello?
Yes,
In-
sir.
Is it clear?
Sir, it's clear. Yes, yes.
Okay. Now attached data will extract all these individual values. That means it will give you individual value of IQ, mental age, anxiety, depression, stress, communication, individual values. Otherwise, they are available in data frame. Actually, your data is a data frame. So individual values are till not available. Please remember, they are not available unless you attach this file. Once you attach this file, or other method was extraction. How to extract? For example, I want to extract, suppose IQ. So I have to write down IQ is equal to data $IQ. Then that variable can be extracted. But if you are using this command attach, everything will get separate value. So I'm using this now, attach data. Attach data means individual values are available. Now, again, this command is same. It's exactly same command. You can see model. I'm writing model 2 because initially that was model, I think. Now I'm writing model 2. You can write anything. You can write your name even. Doesn't matter. So model 2, again, linear model. Left-hand side is that variable which is dependent. Dependent variable is your IQ. And it depends upon mental age, plus anxiety, plus depression score, plus stress, plus communication score, plus convolution, and data will be available in data because your entire data is here. Right? So give this command, and there is no need to write down these things. You can directly go to the summary and you will get a very clear picture. Summary. Now here you can see very important point. So this is the function which has been called. Residuals have been computed. Their statistics, minimum residual, maximum residual, and all that. So residuals are very close to 0. So you can see model seems to be working well. Anyhow, so here is an important point. From this equation, because we haven't says that only significant variables to be included. So it has used the method which is generally called enter method. Enter method will take all the variables one at a time. One at a time. For example, what was our first variable? Mental age. So this is mental age, number 1. Then anxiety, then depression, and last one was convolution. Last is convolution. Now, important point to note in the output is to read this. This is the value of beta naught, this one. This is the value of beta 1, beta 2, beta 3, beta 4, beta 5, beta 6. So you can form an equation from here. In simple linear regression, we were having beta naught and beta 1. But here you are having beta 1, beta naught, beta 1, beta 2, 6. But let's look at their significance. There is no idea of looking at the significance of the intercept. We don't require this intercept significance. Wherever star is marked, that means the value is significant. And that we have to retain in the model. Others not. But look at the mental age. Mental age, this is your p-value. P-value is 2.76 into 10 raised to power 9. So p-value is very, very small. Smaller the p-value, variable is significant. So what do you think? Mental age is significant or not? Yes, please.
Significant.
Significant.
How significant?
Okay, mental age is significant. What about anxiety? Yes, please.
Significant.
Again,
Significant.
significant, because triple star. Triple star means highly significant, basically. What about depression score? Yes, please.
Significant.
Because value p-value is 0.05. But sorry, 0.03. 0.03 is still less than 0.05. Yes or no?
Yes.
So again, significant. What about stress? Yes, please. What about stress?
Significant.
Stress is insignificant because p-value becomes more than 0.05. This p-value is more than 0.05. So insignificant. What about communication score? Yes, please. This is a communication score p-value. What do you think?
Insignificant.
Insignificant. What about convolution score?
Insignificant.
Insignificant. So that means out of the 6, how many are significant? 3. So that means your IQ can be predicted based on only
3 significant.
based on only 3, right? If they are based on only 3, then why to include insignificant variable into the model? Yes or no? Yes, please. Hello.
Yes.
Yeah. So we have to include only 3 significant variables into the model because they are not making any significant contribution. Now, if you remember, there was R square and there was adjusted R square. And somebody has asked me this question, that what is the difference between R square and adjusted R square, if you remember. Yes, madam, aapne pucha tha question. You have asked me this question.
Yes.
Yeah. Okay. Let me explain it to you. Now, first of all, I'll update the model. Now, update means removing these insignificant variables. Yes or no? Yes, please. Because they are not making any significant contribution to predict. So this is the model. So this was our model. Now update this model. Update model, the same model, model I2 minus tilde minus. You remove stress, you remove communication score, you remove convolution score. So I have removed with minus sign. And that is upgradation of the model. Run this model and summary model. You can see now only significant variables are retained in the model. Can you see that? Yes, please. Hello.
Yes, sir.
Yes.
Now, this is significant. This is significant. Forget about intercept. The mental age is significant. Anxiety is significant. Depression score is significant. All right. So these 3 are significant. Can you form an equation from here? Yes, please. So your IQ will be equal to anybody, please. We want to form an equation.
Minus 13.66725.
Minus
66725.
13.66725. Yes.
Plus 0.7016.
Plus 0.070 162 multiply by mental age. Let me write MA for mental age plus, yes, please.
0.9058.
90582 multiply with what?
AN anxiety.
Anxiety. I'm writing simply AN plus, yes, please.
4.62739.
62739 into
DS.
let me write the depression score. So this is your final equation. So IQ can be predicted based on this. If somebody knows about the value of mental age, anxiety, and depression score, substitute here, you will get the value of the IQ. This is what is the prediction equation. Now there are two important things here. One is this is multiple R square, this value. And then there is adjusted R square. Can you see that?
Yes.
Now, what is the difference? See, very important point. How many predictors we were having? 6. Yes or no?
Yes.
Out of that, how many are coming out to be significant at the final stage?
3.
3. But if you are having 6 predictors, somebody can include the 7th predictor also. Let's say he include height also. He include body surface area also. He include weight also. That IQ may depend upon weight. IQ may depend upon BMI also. He can add more and more factors. There is no harm. Yes or no?
Okay.
Right? So if you are increasing more and more independent variables, remember your R square will goes on increasing. I'm making a very strong point. If you are adding more and more independent variables, your R square will goes on increasing every time. It will never decrease. But adjusted R square will only increase if your additional variables, if your whatever the additional variable like height, weight you are adding, if they are making a significant contribution, that means their values are coming out to be significant, then and only then adjusted R square will increase. Otherwise, adjusted R square will never increase. Only R square will go on increasing. What does this mean? It means that if there is a big gap between R square and adjusted R square, let's say your R square is 0.97, adjusted R square is only 0.6. That means some irrelevant variables are there in your model, or some insignificant variables are in your model, which are not making any significant contribution. Do you follow my point?
Yes.
Right? Let me explain you in a simple way. Suppose there is a very heavy box, and it may be 300-400 kgs, very heavy box, and 4 people are carrying that box, 2 on the front and 2 on the back. So some sharing will be there. Somebody is sharing 80 kg, somebody is sharing 120 kg, somebody is sharing 100 kg. Yes or no? Yes. Right?
Yes.
So that the total comes to 300. So that sharing is basically your R square. Sharing is basically your R square. Right? Now, one of their friend has come over and he says that 4 of them are already there. Let me also support them. And he stand in between. And by standing in between, he is sharing some load. And let's say this time he shares 20 to 25 to 35 kg. But still sharing is there. So R square will improve because one additional person has come. So that is your R square will increase. Right? Then another person has come. He says, already 5 people are there. Let me also put my contribution. So now there are 2 on the front, 2 in the middle, and 2 on the back. This 6th person may be sharing 10 or 12 kg, but he's sharing something. R square will go on increasing because sharing is increasing. Right? Now the 7th person has also come. Now he's very smart. He says 6 people are already there. But just to show his presence, he says, let me just be attached a little bit. And he put a finger only. Not a hand, he will just put a finger, and finger is sharing maybe 10 to 12 gram. Yes or no? Hello?
Yes, yes, yes.
Yes, sir.
Now, if this 10 to 12 gram R square contribution will increase further.
Yes.
So obviously R square will increase. But do you think the adjusted R square will increase? Because this 10 to 12 gram is not a significant figure. It's not a significant contribution. So this adjusted R square will not increase. This is what it means by that. If you add more and more variable, R square will go on increasing, but adjusted R square will only increase if additional variable is making a significant contribution. If it doesn't, adjusted R square will not increase. So that means we have formed the equation, multiple regression equation with 3 variables. And this is the value of the ANOVA table. ANOVA table value must be significant, right? Then and only then your model is valid. So you have to report this equation number 1, which we have written. I think I have written somewhere this equation. Okay. Here I have written this equation. This equation you have to write down. Then value of R square you need to report. Value of adjusted R square you need to report, right? And the F statistics value with P value as this. This has to be significant because this is basically testing your regression coefficients. Beta 1 is equal to beta 2 is equal to beta 3 is equal to beta 6 is equal to 0. So that is being tested by this F statistics, right? So this is called multiple regression. So this completes your correlation and regression part. And I'll stop here, and tomorrow we'll start with estimation and testing with all practical examples. First, I'll give you a theory and then practical background. If you have any question, you are most welcome to ask, please. Yes, please. Any question?
If you don't mind, if you have time.